Now connecting the angles in the lab reference frame and center of mass reference frame. Most scattering experiments are carried out in laboratory frame, in which the target particle is assumed at rest while the projectile are moving, while calculations are done in the center of mass reference frame, because it is easier to calculate the scattering products in the CM. Now, in order to verify our results, it is required to convert our results from one reference frame to another reference frame. Therefore, we are going to derive equations by which we can transform from one reference frame to another reference frame. To find the connection between the lab and CM cross sections, we need first to find how the scattering angles in one frame are related to their counterparts in the other. We are going to study how these thetas are related in the both reference frames with each other. So for this purpose, let us consider the scattering of two structureless and non-relativistic particles of masses m1 and m2. Here m2 represents the target which is initially at rest, and m1 is the projectile. In this figure, here is the lab reference frame and this one is the CM reference frame. In the lab reference frame, the target is assumed to be at rest while the projectile is moving, while in the CM reference frame, the center of mass is assumed to be at rest while the target and the projectile moves towards each other. So in this topic, we are going to find the relation between theta with theta 1 and similarly with theta 2 and theta. So let me discuss about the scattering in lab reference frame. Here the two particles, one is the projectile, the other one is the target. The velocity before the collision, the velocity of the projectile is v1l in the lab reference frame, while the velocity of the target is v2l, which is 0. After making collision with each other, the projectile scatters with an angle theta 1 and moving now with velocity v1 dash l. Similarly, the target now moves with a velocity v2 dash l and making an angle theta 2. Similarly, in the CM reference frame, the velocity of the projectile is v1c while the velocity of the target is v2c. After collision, the velocity of the projectile is v1 dash c and which is scattered an angle of theta. Similarly, the velocity of the target is v2 dash c and it makes an angle phi minus theta. So to find the relation between theta 1 and theta, if R1L represents the position of the projectile in the lab reference frame, and similarly R1C represents the position of the projectile in the center of mass reference frames, and m1 is the mass of the projectile, and R represents the position of the center of mass with respect to the lab reference frame. Then we have R1L is equal to R1C plus R. Here this is the position of the projectile in the lab reference frame, while R1C is the position of the projectile in the CM reference frame, and capital R represents the position of the center of mass with respect to the lab reference frame. So taking their derivatives, this is equation number 1. Taking their derivatives, so time derivatives of this equation will lead us to the velocities. So the time derivative, taking derivative, this will be V1 L, which is equal to V1C plus VCM. Let's suppose this one is equation number 1, where the V1L is the velocity of the projectile in the lab reference frame, and V1C is the velocity of the projectile in the center of mass, and VCM is the velocity of the center of mass with respect to the lab reference frame. Similarly, after collision, this one is before collision. This is the velocity before collision. Similarly, after collision, the velocities of the projectile in the lab reference frame is related to the velocity of the projectile in the center of mass reference frame is this is equation number 2. Now in components, V1 dash L is equal to V1 dash L cos theta 1, because here the theta of the projectile is theta 1. This is V1 equal to V1 dash C cos theta, because in the center of mass reference frame the velocity of the projectile is theta, plus VCM. This is equation number 3. And for the sine components, this will be V1L dash sine theta 1. This is equal to V1C dash sine theta. And because center of mass in the center of mass reference frame is at rest, so this will be 0. This equation is 4. Now dividing equation number 4 by 3. 4 divided by 3. This will be V1 dash L will be cancelled with each other, so we will get sine theta 1, or we can write it as V1 dash L sine theta 1 upon V1 dash L cos theta 1, which is equal to V1 dash C sine theta upon V1 dash C cos theta plus VCM. This will be cancelled with each other, and sine theta 1 upon cos theta 1 is tan theta 1, which is equal to Breaking this v1 dash c into the denominator, this will be sine theta upon v1 dash c cos theta divided by v1 dash c plus vcm divided by v1 dash c. They will be cancelled with each other, and we will are left with tan theta 1 is equal to sine theta upon cos theta plus vcm upon v1 dash c. Let this is equation number 5. Now to calculate vcm upon v1 dash c, let as m1 as m1 plus m2 vcm is equal to m1 v1l plus m2 v2l, because in elastic collision the net momentum of the system remains 0. So the momentum of the center of mass is equal to the momentum of the first particle plus momentum of the second particle. We assume that the in center of mass reference frame, the center of mass remains stationary. So this is the momentum of the whole system, the momentum of the center of both the particles with respect to center of mass, and this is the momentum of the first particle before collision in center of mass reference frame, and this is the momentum of the second particle or the target particle in the center of mass reference frame before collision. So vcm is equal to m1 v1c plus m2 v2c divided by m1 plus m2, bringing this m1 plus m2 into the denominator to the right side. Which is further can be written as sorry, this is actually not c, but this is the L in the lab reference frame. This is the velocity of the both the particles in the lab reference frame. So we assumed that velocity of the second particle in the lab reference frame is 0. Since v2l is 0, so this one will be m1 v1l upon m1 plus m2, because v2l is equal to 0. Now put this equation in equation number, let this is equation number 6, and put it in equation number first, which is this one. So put equation number 6 in equation number 1, we get v1 L is equal to v1c plus m1 v1L upon m1 plus m2. After simplifying for v1c, we will get v1c is equal to 1 minus m1 upon m1 plus m2. Bringing this term to the left side, it will become negative, and taking common v1l from both the terms, and further this will be equal to v1c will be equal to m2 taking LCM of these two, so it will be m2 v1l upon m1 plus m2. Let this is equation number 7. On the other hand, since we know that the center of mass in the CM reference frame is at rest, so the total momenta before and after collision will be 0. That means that the total momentum in the center of mass is m1 v1c minus m2 v2c. This is equal to 0, because in the center of mass the projectile and the target particles both are moving opposite to each other. That is why this one term is negative. So by simplifying it, this implies that v2c will be equal to m1 upon m2 into v1c. This is equation number 8. And similarly, this one is before collision in the center of mass, and similarly for after collision, this one is p dash cx is equal to m1 v1 dash c cos theta minus m2 v2 c dash cos theta. This is equal to 0, because initially before collision the momentum was wholly along the x-axis, and after collision the momentum, this one is along the x-axis. Therefore this implies that v2 dash c is equal to m1 upon m2 v1 dash c. This is equation number 9. So further, for an elastic collision, the kinetic energy remains conserved. Therefore, half m1 v1 c square plus half m2 v2 c square. This is equal to half m1 v1 dash c square plus half m2 v2 dash c square. By simplifying it, by simplification, there is no difficult task. Take 1 over 2 from left side and right side common, both will cancel with each other, and similarly m1 and m2 will cancel with each other. Similarly m1 will cancel with m1, and similarly m2 will cancel with m2. So after simplification, v1 dash c is equal to v1c, and similarly v2 dash c is equal to v2c. What we have obtained here, in elastic scattering, if the scattering is elastic in the center of mass reference frame, here we see that before collision and after collision the velocity of the projectile is same, there will be no change, and similarly the velocity of the target will also doesn't change. Thus we can write equation number we can write equation number 7 as you can see here. This is equation number 7, and here we obtained as v1 dash c after scattering, the velocity of the projectile in center of mass is equal to its initial velocity, which was given by equation number 7. Thus, as before scattering the velocity was this one, so after scattering the velocity is also m2 v1l upon m1 plus m2. That this is equation number 10. which is equal to v1c. So after this, dividing equation number 6, now divide equation 6 by 10. So this will be equal to, which is here is equation number 6, VCM upon V1 dash C, which is equal to M2 V1L divided by M1 plus M2 whole divided by M2 V1L divided by M1 plus M2. Sorry, this one is M1. As you can see from equation number 1, this is M1. So these terms cancel with each other, therefore VCM divided by V1 dash C is equal to M1 upon M2. This is equation number 11. Now finally we got this value and putting it in equation number 5. Now put equation 11 in equation number 5, which is this one. Therefore equation 5, which is tangent theta 1 is equal to sine theta divided by cos theta plus VCM upon V1 dash C, which is M1 divided by M2. This is equation number 12. So this is our final value, in which we are going to, our job is to find connecting the angles in the lab and CM frame. So here it is the velocity in the lab reference frame, and this one is in the CM reference frame. Or we can also write it in the form, we have to use this one identity as cos theta is equal to 1 upon tan square theta plus 1 whole under the root. So we can also write it as for the label reference frame cos theta 1 tan theta 1. So by using this value we can simplify and can write it equation number 12 as equation 12 would become cos theta 1 is equal to cos theta plus m1 upon m2 divided by whole under the root 1 plus m1 square upon m2 square plus 2 m1 upon m2 cos theta. So this is equation number 13. So you can use equation number 12 or equation number 13 in order to transform from one reference frame to another reference frame, so for the scattering angle of the projectile. So this was the relation between theta and theta 1 as shown here in the figure. This was the theta 1 and this was theta. In order to transform to find the results in the center of mass reference frame, and we have to change it into the lab reference frame to check our results. Now we are going to find the relation between the theta 2 and theta. So relation between theta 2 and theta, which is the scattering angle of the target in the lab reference frame, and it is the scattering angle of the projectile in the center of mass reference frame. So by similar fashion, using equation number 2, from equation 2 we can write as v2 dash L is equal to v2 dash C plus vcm, and similarly resolving it into x and y components. So their x and y components will be v2 in components v2 dash L cos theta 2 is equal to minus v2 dash C cos theta plus vcm. The negative sign is because of in the center of mass reference frame the target particle was approaching towards the left, and further we can write it as minus cos theta plus 1 into v2c dash. This is equation number 14. I have written v2c dash because in equation number 4, sorry, equation number, because vcm, which we already derived, was v2 dash c, and it was also equal to v2c, because in the center of mass reference frame we proved that the velocity of the target before and after scattering was the same, and it was equal to the center of mass velocity. So I have used v2 dash c instead of vcm as from this equation. Similarly, for the sine components, v2 dash L sine theta 2 is equal to minus v2 dash c sine theta, because in this figure, if we find the distribute the resolving these two velocities into components, so they are opposite to each other. So this one was positive, this was negative, as in this equation, and similarly this one will be positive and this one is negative because it is downward. This is equation number 15. By combining these two equations, equation number 14 and 15, I will only write the result, which is tangent theta 2. It is simply by dividing equation 15 by 14. So this one will be equal to sine theta divided by minus cos theta plus VCM divided by V2 dash C, and further it can be written as sine theta divided by 1 minus cos theta, because V2 dash C is also equal to VCM, so they will cancel with each other and we will be left with one only. And this one is now equal to cotangent theta upon 2, and theta will be theta 2. Similarly, this one is, this implies that this is tangent theta 2, and this implies that theta 2 will be equal to cotangent theta upon 2. Sorry, this one theta 2 will be equal to phi minus theta upon 2, which is the last result. Question number 16. Thank you very much.